Hi, welcome back to AP Physics C, Electricity and Magnetism, Unit 3, Circuits. So prior to this video, we've been focusing on just simply resistors and circuits. So now we're going to focus on capacitors and circuits. So remember, capacitors are devices that store charge. So we're able to do that via a circuit, which then later in the, here in the next video, we're going to look at what happens when we put resistors and capacitors in circuits. But we need to know some of this basic information about how does a capacitor behave in the circuit. So capacitors, again, just like when we talked about equivalent resistance, capacitors will have their own equivalent capacitance equation for a series capacitors in series and then capacitors in parallel. So up here, these are our capacitors in parallel, right? Again, because they have paths to take down. And then this is in series. Right, I know it's a little bit of a weird picture. In fact, this is a parallel capacitor picture, right? So capacitors in series would look much like if they're resistors, right? Something along the lines like this, right? So they're connected to a voltage source. I know I'm kind of drawing into that diagram below. So I have a voltage source. I have C1, C2, C3, okay? So for a parallel circuit, individual capacitors act as one large capacitor storing a large charge resulting in a total capacitance that is simply the sum of the individual values. That's the picture that I kind of scribbled out, because what you can do is you can replace these three capacitors with this line of capacitors that has the same equivalent capacitance, okay? And so we say Q equals CV, and what happens is, much like series circuits, right, these capacitors will have the same voltage going down these lines, right? Which means if these are all the same, that means I can simply add up for my Q total to be the sum of those capacitors. So the equivalent capacitance in parallel is simply C1 plus C2 plus C3 plus ... right? So all those equivalent, that's the equivalent, what is called equivalent capacitance. So for a series circuit or with capacitors, it's a little bit trickier, okay? Again, if we look at Q equals CV, what happens is down these, down the paths, right, it's going to have the same charge, right? And so Q equals CV, right? And I know from Kirchhoff's rule that the charge, or sorry, the voltage has to be equal going across those capacitors. And so that tells me that Q total, right, over all this. And so that tells me that the equivalent capacitance is going to be that kind of inverse looking relationship that we saw with like parallel resistors. Okay, and it comes from, again, Q equals CV. Now, in a DC circuit, an initially uncharged capacitor will begin to store charge on its plates, increasing the potential difference until the voltage of the capacitor equals the voltage of the power supply. At this point, right, there's no current that's going to be passing through the capacitor, and it acts as an open switch until you finally make the decision to discharge. And we'll get into that when we talk about the RC circuits, okay? At this point, it's what we call a steady state, right? And so that's kind of when you get in an equation like Q equals CV, right? Q equals CV tells us that it is a steady state capacitor circuit. All right, so let's look at an example problem when it comes to these capacitance. And so we're going to assume that these are going to be in series, right? So you say find the overall capacitance and the individual RMS voltage drops across the following sets of two capacitors in series. There it is again. When connected to a 12-volt alternating current supply. So A, the two capacitors each will have a capacitance of 47 nanofarads, which 47 nanofarads is 47 times 10 to the negative 9th farads. And then B, one capacitor of 470 nanofarads connected in series to a capacitor of 1 microfarad. So this would be 470 times 10 to the negative ninth farads, and this is 1 times 10 to the negative sixth farads. Okay, remember the unit for capacitance is farads, F-A-R-A-D-S, right? Named after Michael Faraday, right? So that's our capacitance unit. All right, so part A. I'm going to split this into two. So if we want to find the equivalent resistance, because they're in series, we're going to do 1 over CEQ equals 1 over C1 plus 1 over C2. This one's a little bit easy because we have the same capacitance. So 1 over 47 times 10 to the negative ninth plus 1 over 47 times 10 to the negative ninth. And it's going to essentially be 2 over 47 times 10 to the negative ninth. But we flip it, and so we get 47 times 10 to the negative ninth over 2, or simply put 2.35 times 10 to the negative eighth farads. Right, so that is my equivalent capacitance. What that then allows me to do is to solve, right, is to use my Q equals CV to find how much charge do I have going across there, right? Because I can't do anything, I can't find the individual voltage until I find the total charge. And so it's going to be 2.35 times 10 to the negative eighth farads times 12 volts. And it's going to give me 2.82 times 10 to the negative 7, coulombs. Right? And so that's how much charge that's going across each capacitor. Right? And so this is actually, again, pretty simple. I just do Q over C, equivalent, and so they're equal, they're the same capacitance. So I just find, if I find one, I find them both. Yep, that's charge. And then capacitance, 47 times 10 to the negative ninth farads. So voltage is a coulomb per farad. So 2.82 exponent negative 7 divided by 47 exponent negative 9. And so I get a total voltage of 6 volts. Is it kind of what we expected? Yes, because I have two equal capacitors with 12 volts. It should split evenly. All right, so now let's do part B. Now we have one capacitor at 470 nanofarads and another at 1 microfarad. So again, equivalent resistance, 1 over C1 plus 1 over C2. So 1 over 470 times 10 to the negative ninth plus 1 over 1 times 10 to the negative sixth. Okay, this will give me something over times 10 to the negative something, right? And then when I flip it, I get 3.19 times 10 to the negative seventh farads, which is 319 nanofarads, whichever one you want to call it. So there's my equivalent equivalent capacitance. Now I take that number again, Q equals CV. And so I'm going to solve this so I have 3.19 times 10 to the negative seventh times 12. Again, this step here, what's in orange, allows me to find the total charge that is going to be stored on those capacitors. And so I get an a total charge of 3.84 times 10 to the negative sixth coulombs. And now I can find each individual, voltage. So V equals Q over C. So 3.84 times 10 to the negative 6 coulombs over 470 times 10 to the negative ninth farads. And so that gives me a voltage of 8.2 volts. And now I find the next one, again, Q over C. So 3.84 times 10 to the negative sixth divided by 1 times 10 to the negative sixth. And it's going to give me 3.8 volts. So these two should equal to 12 volts, and they do. So 8.2 volts plus 3.8 volts does equal 12 volts. Okay, so we're going to enter into the last video. We're going to take the resistor circuits, capacitor circuits, and combine them into the RC circuit to finish out the